AI has almost no chance of breaking cryptography. Think of a hash function. You take in an input and you just mash it together and you get out a random looking short string of characters. And AI can't really predict that because one single change in an input in a hash function completely changes the output. But for AI, similar inputs lead pretty similar outputs.
Scraping Bits is brought to you by the following sponsors: Fastlane Labs, Trustless MEV. MEV Protocol. Maximize your ETH staking value with MEV exclusively on mev.io. And Composable. Execute any intent on any chain. Coming soon to mantis.app. That is mantis.app. GM everyone. My name's DeGatchi, the host of Scraping Bits, and today I have another special guest, Porter from Matter Labs. How's it going, friend?
GM, it's good. I'm excited to finally get to talk to you.
Finally, yeah, we had been delaying it for so long. But, we're finally here, and we get to talk about cryptography in the ZK realm. Just for the people that aren't familiar with you, who are you and what do you do?
Yeah. My name is Porter. I work at Matter Labs as a security engineer. Matter Labs is the company that works on zkSync. So pretty much people just think I work at zkSync. Within the company, I'm on the security team, and specifically I help with a lot of our cryptography. So auditing the actual ZK code that makes zkSync an L2.
Interesting. How did you even get into this? This is a very niche thing, being able to audit cryptography. What made you go down this path? And how did you really get into all of this?
Okay, so the full backstory is when I was really little, I thought pretty much just codes and code breaking was like the coolest thing you could do. And so I was always into like secret messages and then cryptography. And obviously that ended up leading me here.
There's got to be like a lot of math involved as well. Did you go to uni to study math with cryptography, or did you just do self-taught?
Yeah, I went to Harvey Mudd College outside of Los Angeles in the United States, and I studied math and computer science.
Okay, interesting. Damn. How did you make your way into zkSync then? You mentioned before this you were doing Solana auditing. I think that's quite different to auditing cryptography.
It is a little bit different. So yeah, when I first got into like the crypto industry, I was at a company called Podolsky Security, and we did a lot of the like early audits in the Solana ecosystem. And I mean, I just kind of signed up for a crypto job. I didn't know like what to expect. I didn't know much about Solana at the time. I didn't know like really anything. But I had always had that dream since I was a kid of doing more cryptography. And so I asked continuously to put on like any of the projects that have more math or any of the projects that actually roll their own cryptography. One thing led to another, and eventually I ended up at Matter Labs. So
what do you think is a prerequisite to being able to get into cryptography auditing? Obviously, you know a lot of math, you know cryptography, but to what degree? Those fields are practically infinite if you want to go master each topic in each of them, right? What do you really need to get into this kind of stuff and to start applying and become practical?
Yeah, I was just giving a lot of people this advice because zkSync did like a $1.1 million bug bounty contest.
Yeah, I saw that. Insane.
It was crazy. It's so much money. I still can't believe we did that. And part of what was cool was that the first time there's ever been ZK circuits included in the bug bounty. And so a lot of people were asking, how do I get started? And I think there's always kind of two good ways to learn something. And you should probably do some combination of both. One is just like look at bugs that other people have found before. Just read previous audit reports. Look at ZK bugs that have happened in production to other companies and stuff, and then try to find those same bugs inside zkSync. And then the other is really understand the protocol and what's supposed to be happening. And if you can do that, then sometimes it's really obvious what's missing.
Yeah, 100%. You have to understand the underlying architecture and all its game theory, how it all interacts with different parts of it. Did you do much smart contract auditing within ZK as well, or did you just really focus on actually building the L2 itself?
Mostly, at least at zkSync, like all of our ZK is focused on building the L2 itself. We don't do too much at the application layer, although I think that there's tons of cool application layer ZK projects. I mean, like Tornado Cache was one of my favorites.
I wonder your opinion on the advancement of ZK chains, because when you think about something like Tornado Cache, right? They got sanctioned, put in prison. But now there's these entire chains dedicated to enabling basically the same thing. And I guess it depends on whether the company is completely decentralized or not, as in people can run their own nodes like Ethereum, or if it's just a centralized entity. But if it is decentralized, right, it's a major red flag for governments and regulators. Because, if you just sanction Tornado Cash, now you have an entire chain of the equivalent things, which is, great for us, but horrible for them. So do you have any spicy takes on that?
One is that Tornado Cash is still running, it's still there. You could still use it.
Yeah.
They can't really stop it. And then in general, I just think governments are always going to be on the losing end of this back and forth battle, because you just have to find one country that's okay with everything. And there's so many, for example, small island countries who would be so happy to have all this revenue and stuff. They would love to change their laws to make crypto very acceptable.
Interesting. When building out the cryptography, right, in zkSync, but what are some potential vulnerabilities, associated with the implementation of zero knowledge proofs in this technology, and how do you really mitigate these vulnerabilities?
Yeah. First is what does zkSync use the zk for is proving the state transitions. So moving the chain forward. And so if there are flaws in that proof, then you can prove bad state transitions. You could prove, for example, that all the money now belongs to you, or pretty much anything else. It's kind of crazy. Almost any bug inside of the ZK code quickly becomes critical, unless there's external checks that are not part of the ZK system.
Yeah, and I feel it'll be really hard to find it, no? There's just so much rigor that goes into it. And when it does come up and running, right, then imagine it just going on for months or years, and then eventually you find an exploit and you're like, oh shit, someone can just completely screw up the entire network and give themselves tons of money or screw other people over. How do you even manage to go past from that when you find something? You just have to spin it up again, or what happens?
So I have a fun example of that. Well, when zkSync, first of all, we don't use privacy, and so we would at least see something bad happening. And for the moment, we do have a 20-hour execution delay, which means pretty much we have 20 hours to notice something, stop it, go back and fix things. Hopefully, we never have to use that, but it is there as a safety feature for now. But eventually, we're going to remove it, and thing like that happens will just happen. But the story I wanted to share was from Zcash. So Zcash is actually private, and in the first version of their ZK code, have you ever heard of trusted setups?
I haven't, no.
Okay, so some ZK algorithms require you to basically, there needs to be some secret that no one in the world knows, and so everyone kind of adds a little randomness into the pot, and then hopefully if enough people do that, then the pot's pretty random. Anyways, Zcash found a bug in their trusted setup program. Because everything on Zcash is private anyways, there's no way to know whether this was ever exploited or what happened.
Oh.
It's a complete mystery whether this was caught or done by malicious people before the actual developers from zkSync, an electric coin company, fixed it.
Damn, that's really interesting actually. So why didn't zkSync go private? Why did they not go that route?
I do think we want some privacy eventually, but for now the goal is just scale Ethereum. Ethereum's not private, so default scaling Ethereum doesn't require privacy yet.
That makes sense. Yeah, if you go private, just completely 180 is the inherent vision of it, which is complete transparency, right?
Yeah, I don't know if that needs to be the vision. I don't know if complete transparency is actually that much of a feature. I think it maybe partly is just a bug. Satoshi even commented on foreign posts. He would have made Bitcoin included ZK privacy if it was more advanced back in the day.
Oh, that would be good though. I would totally be down for an Ethereum ZK based model where basically everything is private. That would be an insane arena though. Imagine all the black hat activity on a complete private chain, all the MEV. I don't even know how that would work though. If the transactions are private, right? Then would MEV even exist?
That is a question. Sometimes you can guess which transactions are coming, even if you don't know for sure. But anyways, all this Aztec's building this, so we're gonna get to see this in real world soon.
Yeah, I'm super keen for Aztec because they have a public and private mempool. It's kind of a mixture of both. But yeah, it's gonna be super interesting, I think. I was talking to Uri from Blockstrat just yesterday. I mentioned this as well with him. If you have this system where you can't see the actual transactions, the details, no call data, you only see the value. And then you have the block builders, and you order them in a way where you always put the highest in there and not bias towards the transaction to create MEV or enable partners that do MEV. I wonder if that would be an interesting scenario. But there, again, it is a game that if there is MEV to be captured, then you could theoretically create some system to kind of guess which transactions would be ordered in different ways. I don't know, maybe based off the time it was submitted, or maybe the value indicates something. Even though it's scarce information, there's not really much feedback to be had. It might be an interesting concept, and I guess you never know until you really try it, to be honest. But it was just something that popped up.
MEV is terrifying. I think it'll always exist at least a little bit in some form.
I think MEV without private transactions is actually quite, I think, interesting. It's a tough game, but I like the arbitrages. Those are good for the market. But front running and sandwiching probably isn't the best. You don't want to have that in your model of, where we're trying to replace CeFi, right? You're getting front ran every single time you do a swap. It's just built in. That's a feature. It's not a bug. What do you think where the industry is moving, and versus where do you think it needs to move? Now, you've kind of got two perspectives. You got like the ZK realm and the traditional L1 and normal L2s, but you kind of hit them all now. So what do you think from a macro point of view the industry really needs to go towards, and where it's moving right now?
Yeah, that's a great question. I think first, the cryptographers, I think in general, are doing great work. Zero knowledge cryptography has gotten so much better and so much faster, and there's still like lots of new ideas being pushed. And I think the cryptographers are doing like really well, like completely like going in the right direction. The rest of the industry, or the industry overall, I don't know where things are going to end up. Everyone's competing on all these different metrics, but then like, these completely like random chains have tons of money and tons of users in other parts of the world and stuff. So
I'm very interested to see ZK bridges and maybe even cross-chain interactions of L1s interacting with ZK L2s, and maybe even some kind of conglomerate of all of them intertwining like a web in some ways. I know there's a few people like Composable that's doing a cross-chain kind of aggregator, and I think the bridging system is really needed because it's all spread across multiple chains, the same liquidity pools. It's so weird, but that's just kind of something I've noticed. And then you've got the MEV game, so people are trying to screw people over for a small amount of money, just screws the user over. And then you have like the inherent hacks. If you invest or you become an LP provider, right, you're kind of just getting screwed over because people just perform JIT on you, so you actually exit liquidity. And like in the inherent hacking of contracts, they're all 0 days, probably on, let's say, 1% of the contracts out there, but they're 0 days, so you never know until you go through all of the possible options. That's why you need a fuzzer or some kind of AI fuzzer. Probably an AI fuzzer, because I was building a fuzzer, and the amount of combinations you can create is infinite. You need a lot of compute to do it, and just the amount of options there are. Like when you change one variable, it creates a whole chain reaction of possibilities. So I think AI is actually needed for large scale cybersecurity and blockchain. Even in general, though, speaking of AI, and in the realm of that, do you ever think it would be able to crack cryptography? And what are your thoughts on like quantum computing as well, since that is really in the realm of, if it is able to crack it, then kind of the world collapses in some ways until there is something better than what is crackable?
I think AI actually has almost no chance of breaking cryptography. There was even a scare like a month ago when Sam Altman got overthrown from OpenAI. And people were saying internally maybe that like the AI had cracked cryptography, and like that was like what was spooky and it was going to destroy the world. And even just think of a hash function, which is one of the more simpler pieces of cryptography. Like you take in an input and you just mash it together and you get out a random looking short string of characters. And AI can't really predict that very well, because one single change in an input in a hash function completely changes the output. But for AI, similar inputs lead to pretty similar outputs normally. So
yeah, there isn't like really any pattern towards it. It's just, or maybe there is and we just don't really know it. But yeah, the smallest input completely changes the entire thing. And computationally, it would be very difficult to crack something with a lot of characters. But you never know.
Yeah, like you can't do it by brute force. So the AI would have to notice something unique that no one else has noticed.
Yeah, I think it is possible. It's really specialized in finding patterns, right? So maybe those are, I think it is the best hope at it. than humans, at least. If it can just live on for, because we just die after X amount of years, but computers can virtually live on forever, right? If you just hook it up to internet, hook it up to like a solar panel farm and just have infinite compute, right? I don't know, it can just live forever. So maybe, we'll see. Yeah, that'd be a crazy world to live in if it does crack it though. That'd be like a giant collapse. But man, can you explain the cryptographic principles that kind of underpin zk proofs and how they ensure privacy and security in blockchain applications for the people that aren't really familiar?
So it really starts actually from error correcting codes. I'm surprised like more people in zk don't kind of talk about like the history of where this came from, because I think like error correcting codes are very intuitive. It's if you send some data and like what happens if it gets kind of corrupted halfway like across being sent, are you able to like correct the errors yourself on your side, or do you have to ask me to like resend the whole file? And where this is particularly important is like, I don't know, let's say we send like some satellite like way out in space and it's taking a picture and it's gonna like send it, light years back home. We don't want to have to ask that satellite to like resend the photo.
Yeah.
Like, the back and forth is going to be like egregious. So instead, like a naive error correcting code algorithm would just be send me the whole message 3 times in a row. Now, that's kind of inefficient because you're kind of sending a lot of extra information. But if there's just like one error somewhere along there, like 2 of the messages are the same, so you can decode and you're good. This is kind of a long background, but that's like should give a lot of intuition. So then bringing that to zk, what we want to do is prove that some computation was done correctly, and you want the verifier to be able to check it very, very easily. And so actually pretty much all that zk codes and circuits do is you encode the computation and then you do error correction on it, so that if there are any errors, instead of doing error correction, you kind of do like error amplification. So if there's an error in the computation, it ends up affecting like everything else, and then the verifier can catch it very easily. That's my explanation.
Okay, and I guess what are the practical limits of using the proofs as well, I guess in terms of transaction speed and resource requirements?
Yeah, so the overhead of zk right now is about like a 1 million x. So if you were to do some normal computation compared to like doing it with zk, it's about 1 million times worse. So what's beneficial is that the verifier doesn't have to do that work. You can put all of the like hard work on just one prover somewhere in the world.
But wouldn't that be centralized? I guess it doesn't matter. Well, doesn't
as long as the verifier is decentralized, because the prover can't cheat, like because the verifier like knows what's coming and will only like verify valid proofs. So you don't have to trust the prover really at all, actually.
Okay. Can anyone spin up their own prover? I guess, does it have to be centralized?
Yeah, it's called decentralizing the prover. We haven't done that yet for zkSync, but it's relatively straightforward to do. You just let anyone submit the proof to the L1.
Oh, okay. Then someone just picks it up and then kind of does it.
And so like you can do some like fancy designs around like who picks it up and like making sure somebody's doing it, taking turns. You can offer rewards for whoever does it first. But relatively, like, yeah, it's relatively straightforward. Just the decentralizing the prover part of decentralizing L2s.
Okay, interesting. Well, I mean, what does the prover do, and what happens after that with the verifiers?
Yeah, so the verifier is like a smart contract on Ethereum, and it ahead of time has like a verifying key, which is like so it knows sort of what the circuits look like, and it knows kind of like what should be coming. So it knows how to do its checks properly. Besides that, like anyone in the world, anywhere can just generate a proof of the recent transactions and like add it onto the front of the chain. And then the verifier checks the proof. And once the verifiers check the proof, that's when zkSync like officially updates to the new state.
Interesting. Update to the new state. Why do they have to be on chain though? Like the verifiers? Can't it be off chain?
Right. Like in theory with zk, you can put the verifiers anywhere you want. Like you can verify it on a cell phone, but for like the purposes of an L2, we want Ethereum to be checking everything, and so we put the verifier on Ethereum.
Okay. Oh, okay. So it's just like the verifiers are all on Ethereum, and you kind of offload it all onto the prover on the L2, right? Oh wait, that's not the L2.
Yeah,
Is it the L2?
I'd say like the prover kind of goes between. It takes the everything from the L2 and sort of proves it to the L1.
Okay, but then they still have to send. I guess when you're doing like this L2, you're sending all the transactions to the L2. Wouldn't that cost gas in itself though?
Yeah, there's a little bit of L2 gas.
But it still comes out more efficient than actually just confirming it all on the L1, right?
Yeah, I mean, I'm not actually sure what Ethereum transaction fees have been recently, but zkSyncs are about like 12 cents now, 10 to 12 cents per transaction, which is good.
Okay. I mean, yeah, I guess it depends on the time. Like during the bull market, it's ridiculous. Like you pay, I mean, I was paying $50 per transaction. So, it seems all right. It seems like a decent benefit. I see the word like zk snarks and stocks. What are the difference between them? Yeah, never really gone too deep into the zk world, but I hear this all the time.
Yes, this is a hot topic because even the cryptographers love to debate this. So
Sick.
the words stark and stark, obviously like the T and the N are different, but also the leading S is different. So stark stands for scalable, transparent argument of knowledge, and stark stands for succinct, non-interactive argument of knowledge. That's just the definitions. In practice, there is a slight difference, like a meaningful difference in the cryptography, where like starks, I think, allow the verifier or the proof size to be like a little bigger, or the verifier can be like a little slower. But for my opinion, like for most of the general world, everyone should just think of starks as a specific type of snark. I think starks are like the general category, and starks are just like a specific instance. And there is like a minute niche cryptography difference why starks technically sometimes might not be snarks, but it's silly.
So when would you use a snark over a stark, and vice versa?
Yeah. So Ethereum is like already has some like elliptic curve precompiles that make it very easy to verify snarks, because a lot of snarks are based on elliptic curves, and then starks are generally based on hash functions. So in practice, like at least right now, starks have kind of been taking over. I mean, zkSync, we just rolled out our new proof system, Boojum, where we switched to using a stark, or at least fry proofs. And so in practice, what happens is then we do a whole stark proof, but then we want to verify it cheaply on Ethereum. So we actually then prove with a snark that the stark proof was valid. So we kind of like, because you can prove anything, so you can prove that another proof is valid. And so that way, like, people just get the best of both worlds from whichever thing you want.
Interesting. And is this like state of the art, I guess, designs as well? Or is it kind of like AI where people are coming up with new stuff all the time and you're kind of implementing it and seeing how well it works? Or
oh yeah, people come up with new stuff all the time. I mean, like one like recent development has been almost everyone uses what's called prime fields, which are these like large prime numbers that are odd. But normal computers run on like bits, 64 bits at a time, which is not an odd number. And so there's a recent paper from Olatana that's on how you could do snarks over a binary field, which might allow you to do like a lot of normal computations a lot faster. But it's only been like a month since that paper, so I don't know. I think it just got done in practice once, but we'll see like actually how efficient it ends up being.
Because all I see in like the ZK world of, I guess, blockchain, it's all the same stuff. It's like snark, stock, proofs. That's kind of it. I guess not really many people are experimenting, I guess, as much as maybe I'm just not like very naive, not really in the spaces.
Yeah, I would say there's actually a ton of experimentation. It's just all at sort of like minute levels, and it all like counts. There is tons of little differences.
Interesting. What has been your favorite? Have you kind of done your own experimentation at all, or?
I'm biased towards elliptic curves. It's my math background probably, but like, I mean, if you've heard of like Fermat's last theorem and like all his like great number theory things, like the Langlands program, like a lot of big theoretical math problems use elliptic curves and they're very cool. And so I like when elliptic curves show up in cryptography. It's just a completely biased opinion. zkSync has just switched to Starks, which only use hash functions, so we're kind of moving away from the elliptic curves some, but I miss the elliptic curves.
Elliptic curve, I remember that was kind of like my first gateway into just like cryptography in general. I think it was pretty interesting, but then it's like always increasing in like the SHA algorithms, like SHA-2, SHA-3, and you start studying that when you get into, I guess, bytecode stuff. You don't really see it too much, but it is quite interesting. I wonder if anyone's really, I don't know, like, I feel like when you get into crypto, there's a few like routes you can get into. DK was the only one I really didn't get into. I don't know, you can go on like MEV, you can do really low level, like, I guess, bytecode, smart contract stuff, which is also what I did. You can go on the infrastructure play, protocol play, or you go into ZK, or just build chains. I think building chains is quite interesting. You can get a ridiculous amount of funding, and if it does work, I think, yeah, if it does work, then man, you've just built like an entire ecosystem, right? But it's so difficult to build these chains and these ecosystems because you have to build the dev tooling as well. I remember doing something on Hedera Hashgraph, I think it was called, back in the day, and they like modified the EVM, but didn't supply the right, block explorer. You couldn't really look at the contracts on chain at all. You couldn't even get the bytecode, I believe. And like you couldn't use Foundry, it wasn't compatible with it. So they had really no testing ground for forking, and so it made it incredibly hard to test. I wonder, is there anything? What's the dev tooling experience like on zkSync, and are you much involved in that at all?
Yeah, well, because it ends up relating to the proof system. So zkSync is currently language compatible, which means you can take your Solidity, take your Viper, and compile it. And then we have a different bytecode format from what the EVM uses.
Oh,
and
okay.
the reason for that is like mostly historical. It's because when like the founders of zkSync were first trying to build this like 3 or 4 years ago, if you like zk was pretty slow and pretty difficult to do, and so it was tough at the time to directly prove ETH bytecode. It was better to make like a more zk friendly bytecode, and so that's what we have now. But we've realized that you're right, like the whole dev compatibility experience, like block explorers are like so important, and like it's impossible to rebuild how much like dev tooling there's been done for Ethereum. And so we're moving like back towards full Ethereum compatibility now.
When someone does a transaction with the use of ZK proofs, how does it affect the finality of the transaction? And what is like the trade-offs of this? Because, when you think about Ethereum, is it really just similar to Ethereum where you just throw it into a mempool and then like it's not getting ordered, right? So it's not like a block builder is choosing which transactions to put in which order and kind of manipulating it in a way and then sending off a bundle, right?
So the transaction flow for an L2 is, you throw it into the L2 mempool. There's something called a sequencer, which is like our block builder, and that like creates the blocks. And then after the sequencer, the prover like proves the blocks to the L1.
You know what I saw recently? I think it was Arbitrum, or was it Arbitrum? But it was like a sequencer got overloaded quite recently. I don't know if you saw that.
That was literally 2 days ago, those inscriptions.
Yeah, what happened there? Like, I think that's a big point of failure, right? If it's just a single sequencer that's, I guess, centralized, and if it fails, like, what happened there? Then, I mean, what happens? What are the complications that arise after that?
Right. So, our Arbitrum stuff, as a security person, like, I always want the systems to be secure, so I feel bad, like, anytime something crashes, like, it's hard to be perfect. And I'll talk about zkSync. We also had, like, inscriptions yesterday, and I can talk about those, like, what happened with that, too. But first, sequencers, or for the whole L2, the point of an L2 is you don't have to trust any of it. We're not always there yet, but if the sequencer fails, which is the block builder, there's sort of 2 things you should be able to do. One is like from Ethereum itself, you should be able to like create new transactions on Arbitrum. And then also from Ethereum itself, you should be able to like leave and withdraw your money back from Arbitrum. As long as you can do those 2 things, you can pretty much just use Arbitrum through the L1. the fees will be more expensive, but like, at least you can get your money out. And so like no matter what happens with Arbitrum, you should be able to like both enter and leave on your own. So even if the sequencer goes down, in theory, long term, it shouldn't be too much of a problem.
And what happened with zkSync?
Yeah, so I guess in summary, inscriptions are happening, which is like tons of people spamming the chain. Arbitrum first hit like an all-time transaction high for them, and then ended up the sequencer crashed, and it took them like 6 hours to get back online, I think. zkSync, we got hit the next day, and we were going at 150 transactions per second for several hours, which is very impressive because normally we do about 10. We know we can go faster than 10. That's just like what user demand is at. But we'd never actually gone at 150 TPS in production. So it's pretty cool that our system was holding up for several hours. The only thing that happened was we literally had to like upgrade to better hardware halfway through. And so for 15 minutes, we did like a live upgrade. And technically we were down for those 15 minutes. But like all of our code still worked. So I'm counting it like mostly as a win. But technically we did go down too because inscriptions are too powerful. There are too many people.
Yeah, there's two questions that arise. It's, I guess when it goes down, what happens? Is there any like detriment, any, I guess, exploits that could be done to deal with like, I guess, the L in itself? But if the sequencer is like, I guess, the intermediary, then it would just like stop working completely, right? Or is that not correct?
Yeah, I mean, Arbitrum sequencer like couldn't create new blocks, and for the 15 minutes, like zkSync, like users couldn't submit transactions. But because Arbitrum has fraud proofs and zkSync has zk proofs, there's no way for anything bad to happen. Users just like can't really use the chain for a little bit, or theoretically you could use the chain through the L1 itself, but it's kind of annoying.
Yeah, 100%. And I guess, yeah, if you're saying the average was like 10 transactions per second, that was user demand, like 15x that's so unexpected, right? Like it's either an influx of people have converted to zk land, or it was like a targeted event, I guess. But where are the incentives of doing a targeted event? So it must be.
Are you familiar with inscriptions at all? Or I can explain inscriptions.
You're gonna have to explain inscription.
So it's an NFT thing mostly, or kind of a token thing now. And apparently it actually started on Cardano, but really recently it started on Bitcoin. And the point is like Bitcoin doesn't have smart contracts, so you can't really make NFTs, but you can just post blobs of data that have PNGs in them, and then like sort of like monkey trade them. Like it doesn't really like Bitcoin doesn't check or verify anything, so you have to run these sort of like external stuff to check and see who owns what. But that's the idea of inscriptions.
But like, okay, if they're doing that on Bitcoin and you're just sending blobs of data to someone, can't you? Well, what if someone just like copies and pastes it? How do you know where the original came from? Like, what's the value in that? I don't understand that.
Yeah, it's pretty weird. Basically, the Bitcoin itself doesn't track anything. You need to like basically run like an external node that just tracks like who owns these inscriptions. And so it's kind of silly. It kind of makes sense on Bitcoin, but then people started, for whatever like degen reason, which I think it's kind of hilarious. Like I support it, but like go experiment. But like people started doing the same stuff of just posting blobs of like JPEGs on other chains. And so they've been going around one blockchain at a time. Yeah, and whenever like these mints happen, like people just spam the chain like crazy, trying to post all these like NFTs to like, get the mint. Like there's no reason to do that on like a chain that has smart contracts, because you could just do like a normal ERC 721, but that's not what the degens are doing. They're doing inscriptions.
That's so random. Is there even any like financial incentive to, I guess, even target like something like zkSync, apart from obviously getting to the point of verifying and like, I guess, manipulating the prover? But apart from that, is there any other attack vectors that are really aligned with incentives? It just seems not really.
Not too much. Like to really break zkSync, you either need to break our proof system, like find a bug there, and even then we have like some backup checks that you'd have to get past too, or like try and compromise core dev is like another attack vector. But even then, like you have to push some update without anyone noticing, and that's pretty unlikely. These things are getting pretty secure already. I'm actually very impressed with how fast we've gotten pretty mature security-wise.
I wonder how something like zkSync will maintain compatibility with future upgrades. When Ethereum switched to proof of stake from proof of work, well, it's a new upgrade, right? But Ethereum sharding is anticipated, right? Unless it's already implemented, if I'm mistaken. But when it's implemented, how is it going to maintain compatibility with that if it's a big change?
Yeah. So, I mean, like that's one of the challenges is like, everyone talks about like immutability, but if like Ethereum itself keeps changing and then there's an L2, like we want to stay compatible with that. So we're going to have to keep changing. Where does it end? So I'm not exactly sure what it looks like super long term. I think in terms of security and decentralization, I think almost everything about L2s is solved in theory. We need to do a lot of stuff in practice still. The last thing to like solve in theory is that long-term keeping up with Ethereum. How do you do upgrades? How do you do governance and stuff? It's going to be tough.
I wonder, when we talk about the sequencer, actually, I was just thinking, if that's a centralized entity, couldn't there be decentralized versions of it as well? Kind of like the equivalent of block builders on Ethereum.
Yeah, within like all the L2 protocols, this has been the hot topic for the last several months, decentralize the sequencer. And it's kind of interesting because like the reason to decentralize the sequencer is the same reason you want like decentralized block builders on L1. It's for the censorship resistance, but also like, we want these L2s to be able to go like much, much faster than L1. And at some point, if you're just rebuilding everything that L1 has, you're going to end up at L1 speeds. And so it's kind of a little tricky to like decentralize a sequencer while keeping like speeds very high in practice, but I don't think any teams figured it out yet.
What if it was already decentralized by nature, but you ran your own sequencer as a default? Well, then it'll be the exact same thing, but with the ability to have decentralization.
You mean like any user could run their own sequencer?
Yeah, exactly. Like, I guess it would be the same as block building, where I guess a perfect example is like flashbots, right? They created flashbots and then they run their own builder and relayer. And it's not centralized because you can basically spin up your own, and people can send to other ones as well. So there is like a centralized aspect. It's kind of, there's also the option to not choose that entity. So maybe that's an option, because then you have your own sequencer, which could, doing the 150 transactions per second. But then there's also the option for someone else just to have the decentralization aspect. Because imagine if the company got like hit by a government and regulations came and they had to shut down. Well, now the sequence is gone, and then the whole thing's completely gone. But I guess it depends on how much, if the entire like stack is decentralized, it's capable of being decentralized. But it's just food for thought, I think. And it would actually be super interesting to see what like a block builder would be like with a sequence, because now there's just a new kind of MEV game, which I'm always interested in about the game theory behind that. It's just block building for L2s. I wonder if that's a thing though.
It's something like I don't think I've ever been asked, and I don't think anyone ever asks. Maybe it's like a forbidden question for L2s. But if you wanted to know, zkSync just does like first come, first serve like transaction ordering, because we don't want to be like accused of like meving our own users. But some people say like, because for the moment, like each of these L2s is pretty much the only entity running their own sequencer. And so like each of these companies is doing all the block building themselves. And so like we can front run all of our users and make tons of money. But obviously we don't want to do that. So that's another reason to decentralize the sequencer, is it actually spreads out the MEV a lot more instead of having it just be us.
That's a crazy thing. So I think like the L2s are like the biggest, I guess, gas consumers on the network. And obviously they have like insane. Imagine partnering with like an MEV team. It would just be ridiculous, like obviously it would be completely wrong because it's a centralized entity just like completely destroying, front running everyone. It's a good game plan. Nobody noticed because it's all, I guess it's not private actually. If it was private, that would be quite a good game plan, but it's not. But yeah, I don't know. That'll be really interesting to see play out. Who knows? Maybe someone does it, spins up a layer 2 for the ulterior motive to front run everyone.
Yeah, I think like if FTX had their own FTX chain, they probably would have done it.
Oh, 100%. Oh god. I think that's good food for thought though. I don't know if anybody's really talked about that before. I really am interested in like the ZK MEV though. Like if you find, even if it's not private, I don't know, anywhere where there's like, I guess something similar to a sequencer or order flow being sent to something else, there's always an opportunity there somewhere. But
Yeah,
I mean, I'm also wondering, like, how would you even do auditing on like cryptography? Can you even run like a static analyzer or a fuzzer? Like, can you build tools for this stuff, or does it have to be completely manual?
yeah. Well, first I want to answer about the zk MEV a little bit. So the reason like Aztec and these other chains have both public and private states, because if all state was private, like there's nothing for you to interact with. Like there's no you need some shared state between multiple users, and so like you need that to be public pretty much. And so what this means is like if you're all trading in a DEX, your transaction's private and like the other transactions in your same block are all kind of like blended together with yours, but the price is known before your block and after your block publicly. And so like within a block, you're kind of maybe safe from MEV because no one can tell, but like there's still some MEV that could happen like between blocks.
I remember hearing from a Control C, Control V, I think it was a while ago, but you mentioned like L2 MEV where you could convert L1 and L2, I think, if I remember correctly. This was a couple months ago. Yeah, you mentioned something along the lines of like L2 and L1 block building MEV kind of thing, where if you have a block builder and I guess you have like these tokens on L2s, I can't remember correctly, but you could basically predict which blocks were going to be accepted and kind of, I guess, monopolize it in some way, of being able to confirm 2 blocks on different chains, one on each chain, and kind of make a chain of them to perform like cross-layer MEV, which I thought was really interesting. I never really thought of that, but maybe there's probably some game theory that you could mess around with that is similar to that, you know? It does require some expertise, though, obviously, of very niche skills and domains. So.
Yeah, it's pretty cool. I think we actually hired some researchers recently from some college students to think more about these types of problems.
Oh, nice. Well, what have they discovered? If you can share it.
I think it like just started. We just like announced, or we just like accepted them like a few weeks ago. I'm not even sure if it starts until the new year, but the research team hired like 20 college students or something.
Just like a whole class?
Yeah, I mean, I don't know if they're even all college students. Like it could just be anyone, but we just like accepted research proposals recently. And I know one of the big topics was like L2 MEV.
Yeah, cross-chain, cross-layer would be crazy. Combine them all together. Damn, that'd be pretty interesting, but obviously very difficult. I think the hardest thing is like the bridge interaction. I think like with cross-chain and anything similar to it is, you know, you need some kind of way of interconnecting them or connecting them, right? And if you're just going for a bridge like multi-chain, well, first of all, centralized entity, I think they got done for something a while ago, but you know, but then it's like also really slow, you know. And if you're doing something on like chain A and then chain B, or you know, layer 1 and L2, you have this like time delay of whatever it is, and I guess if it's running on that other chain or whatever, then it might just be like gone if there's like a race condition. So then you're left off worse. Like risk management is just out the window. I don't know, some kind of stuff I've thought about in ways, but I think a lot of people talk about cross-chain MEV, but I don't know who's actually doing it because it seems really, really difficult. Who knows if it's even feasible?
Yeah, I'm not sure. Bridging like always one of the big problems.
Going back to that question about the auditing cryptography, can you even make tools? I assume the best tool would be formal verification for it.
Yeah, the dream is to formally verify all your cryptography, but the zk landscape changes so quickly, and you have to change your code every time Ethereum updates that it's actually like not that worthwhile to like Like you want to formally audit something that's just not going to change. Like it's just going to stay the same for a long time.
Right.
And with all the updates, it's kind of tricky to do that.
You
Pretty
just
much
need to be
all.
gold
But
tier math.
yeah, I mean that does help. But you are able to make like custom security tooling specifically for zk. I know Veradice is one company who's done very well in like trying to formally verify some zk things, also doing some fuzzing, and in general just like static analysis of like zk code to look for like different types of zk bugs.
Interesting. I guess it would be different if you're running circuits and you have to kind of audit those. Yeah, I don't know. Interesting. And you're saying it's different bytecode as well. Like, how's it going to be different bytecode if it's all hexadecimals? Are you just not using hexadecimal?
Yeah, I mean, it still ends up being hexadecimal, but like different opcodes from Ethereum.
Yep. Okay, that makes sense. I thought it was like an entirely new machine language. What kind of math do you really need to know to get into cryptography? As you mentioned, the people in that audit, I think it was like the C4 contest or whatever it was. That was a big thing. I remember everyone was switching over to zk, trying to learn how to do it. But I think it's good to upskill into zk, and if you're just stuck in like security, it's always good to upskill into something else instead of being static. So yeah, I guess how would someone, upskill into zk if they're not in it and we're doing something else?
Yeah, so I was very encouraging of people who tried to do this. Like they started like 1 week before the C4 contest, and we're like, all right, I know nothing about zk. Like let's go. I want to be able to like find like $1 million bugs next week. And part of how I broke it down was to like just pick sort of one of the layers. So like the deepest layer of the zk is the math, and like at the very bottom there's like a field on like an elliptic curve. But then building on that elliptic curve, there might be like a hash function. And then like building on the hash function is like the actual kind of like zk protocol. And then like building on like how the proving works, there's like the circuit which describes the code that you're even trying to prove in the first place. And so like each of these layers can kind of like abstracts away the one below it. So you can find bugs in the circuits relatively easily without knowing too much math, because the circuits are just supposed to be describing like, EC recover or SHA-256, like fairly standard stuff. And you don't have to worry about the math layers below if that's not your strong suit.
But it's never not a bad idea to learn math. You can't learn math and be like, oh, damn, I just learned math. What have I done?
No, if you really want to learn the math, I mean, first of all, like just message me on Twitter. I'll give you like all the resources you want. But at a high level, you need like a little bit of number theory, and then like a little bit of like familiarity with finite fields. And
Finite field.
That'll take you a long way. Like finite fields, like modular arithmetic. Clocks go in circles and the numbers repeat after a finite amount. And so a lot of cryptography depends on that.
Interesting. Finite fields and number theory, that should get you a long way.
Yeah. I mean, like a lot of zk ends up just being polynomials and prime numbers. Actually, most of cryptography is like that. You obviously can go really deep, making it sound like simple, but I've studied elliptic curves for years and still don't understand even a fraction of everything that happens with them.
Oh,
but
nice. Interesting. Yeah, I'm like getting into math myself recently, but more towards like methods and probability. But I guess that's towards more like AI and predicting uncertainty instead. But math is great. I think it's super hard to get into if you've never really done it before. But it's just like a language. Well, it is. Yeah, it's just a language. So obviously it's super hard, but you just got to keep doing it every day until eventually you gain some intuition for it. It all clicks, and then you're happy because you're understanding it, and you keep going.
The feeling when it clicks is so good.
Oh yeah, I mean that's what I had when I was learning Rust and all that stuff. Eventually, it just clicks, and you're like, "Wow, I can actually do this competently. This is insane." And man, I'm super happy to talk to you finally after all these weeks.
Yeah, we had to reschedule, but it was super good.
Yeah. Thank you so much for jumping on. I really appreciate your time, and hopefully, the people got something out of this. I know I sure did, and I'm sure we can revisit down the road as well when we both progress in our fields, and hopefully the world is a bit different. Maybe the crypto space is entirely zk by then. Who knows? That'll be really cool. But until then, thank you so much for jumping on. I'll talk to you soon.